Professor Dave here. Let's talk about impulse and momentum. In chemistry, we learned about the conservation of matter. Here in physics, we learned about the conservation of energy. These concepts can be extended to formulate another law, and that is the law of conservation of momentum. Momentum is a term we may be familiar with, but once again, we must learn the rigorous definitions of these words. And linear momentum is defined as mass times velocity, which will be represented by the letter P. Momentum is a vector quantity, as it involves a velocity vector being multiplied by the scalar value of the object's mass. This means momentum will be expressed with SI units of kilogram meters per second. In this case, our everyday use of the word is fairly accurate, and we might say that as a ball rolls down a hill, it will gather momentum. This is true because its velocity will increase as the force of gravity accelerates it towards the ground. The more momentum the ball gathers, the more difficult it will be to bring it to a stop, and an object in motion can therefore have a larger momentum by virtue of being more massive, like a huge boulder, or also by moving at high velocity, like a tiny hailstone or meteorite falling from the sky. If we consider a car in motion, it too will have a momentum equal to mass times velocity, and if you slam on the brakes to avoid a collision, the car will skid a certain distance, because a force must be applied over some duration of time to bring a moving object to rest. The heavier the car and the faster it was moving, the greater this factor will be. A small force acting over a long time could do it, like if you take your foot off the gas and let the friction from the road slowly stop the car. Or a large force acting over a short time could do it, like firmly applying the brakes to the tires. The force that is applied multiplied by the duration of time that it is applied is called the impulse, which will be measured in Newton seconds. The relationship between impulse and momentum is summarized in the impulse-momentum theorem. It states that the impulse, F delta t, is equal to the change in momentum, or delta p, which can also be expressed as mv final minus mv initial. So if you apply some force to push an object for some duration of time, that object will gain a proportional amount of momentum. If an object loses momentum, it must be imparting some force to something else over some time period. Just as the work-energy theorem describes conservation of mechanical energy, the impulse-momentum theorem describes conservation of linear momentum. Another ramification of this theorem is that the force imparted on a moving object when it strikes some surface will be very large if the impact is instantaneous, and much less if the impact involves some time duration. If you fall off your roof onto the ground, it will hurt. But if you fall onto a trampoline, it won't be as bad, because the change in momentum imparted on your body, instead of happening instantly, will be delivered over the entire duration of your contact with the trampoline surface, as it stretches from the force of your fall. This is also why baseball players are taught to swing through the ball rather than stopping the swing upon impact, because if contact is maintained between the bat and the ball for as long as possible, the maximum possible force will be imparted upon the ball. In the case of an object striking another object, total momentum will be conserved through the collision, and the sum of the momenta of the two objects will be the same before and after the collision. The easiest example of this concept involves balls on a pool table. We will often observe that one ball has momentum while the other does not, and after the collision, the first ball has stopped and all of its momentum has been imparted onto the other ball. This type of scenario illustrates conservation of momentum. There is much more to discuss regarding collisions, which we will go over in the next tutorial. Hey, it's Professor Dave. Let's learn about collisions. Whenever an object in motion comes into contact with another object, we can call this event a collision. And this concept applies to balls on a pool table just as it does to tiny molecules or huge celestial objects like asteroids and planets. As we just learned, in any collision there must be a conservation of linear momentum. But this can manifest itself in different ways depending on the type of collision that is occurring. So let's go over these varieties now. First, we will discuss elastic collisions. These resemble collisions between balls on a pool table, where the objects involved remain separate after the collision occurs. With elastic collisions, total kinetic energy will be conserved, as well as the total momentum of the system, so the objects will bounce off of one another with no energy lost whatsoever as a result of the collision. We approximate collisions between atoms and molecules as being elastic when we refer to an ideal gas, just the way we do with billiard balls. There are many other examples of collisions that aren't completely elastic, but we can treat them that way, like when a soccer player kicks a ball, since the player's foot and the ball do indeed remain completely separate after the collision. We would refer to all of these scenarios as examples of nearly elastic collisions, since some kinetic energy is lost to heat and sound in each case. Perfectly inelastic collisions are those in which two separate objects collide, after which they move together as one mass. Sometimes when celestial bodies collide, like two asteroids, the collision is inelastic and they fuse together to form a larger body. In fact, this is how all planets begin to form, including the Earth, over the course of millions of such collisions. When we examine perfectly inelastic collisions, it is easy to analyze momentum because we can treat the two objects as a single object after the collision, with a momentum equal to the sum of the two individual momenta. This is illustrated by the following expression, where m1v1 plus m2v2 is equal to the sum of the masses times v final, which will depend on the magnitudes and directions of the two initial velocities. This approach can also be used to model car collisions, whether the two cars were moving in the same direction or opposite directions. Adding the masses of the cars and combining the velocity vectors will tell us what will happen after the collision. We should note that during inelastic collisions like car crashes, total momentum is conserved, but total kinetic energy is not conserved. Much of the kinetic energy is converted into sound energy, which we hear as the sound of the crash, as well as heat energy and the internal energy of the new system, which allows the bodies to deform as a result of the collision. That's why we call it an inelastic collision. An elastic band always returns to its original condition after being stretched. But with an inelastic collision, things are very different before and after the collision. The amount of kinetic energy lost during an inelastic collision will depend largely on what the objects are and a variety of other factors. In reality, no collision is completely elastic or perfectly inelastic, but is somewhere in between, which we can simply label inelastic, implying that some kinetic energy is lost due to the collision, even if just a little bit. But we can usually approximate a collision as being one of the two extremes, which will simplify the math that must be done in order to make predictions about systems that end up being extremely accurate. This concludes our study of linear motion, which from kinematics and dynamics to harmonic motion and momentum has been quite extensive.